PhD on Deep Learning, organized by E&ICT Academy. So now in this session, Dr. Ashish Tripathi is with us. He is going to take the 2-hour session. So now, before start the session, let me introduce Dr. Ashish Tripathi sir. Dr. Ashish Kumar Tripathi, the senior member IEEE, received his MTech and PhD degree in Computer Science and Engineering from the Department of Computer Science and Engineering, Delhi Technological University, Delhi, in 2013 and 2019 respectively. He is currently working as an assistant professor in the Department of Computer Science and Engineering, Malviya National Institute of Technology, Jaipur. His research interests include computer vision, social media analytics, generative AI, image analysis, and natural language processing. Dr. Tripathi has published several papers in international journals and conferences, including IEEE Transactions. He is an active reviewer for several journals of repute. So now I hand over the session to Dr. Ashish Tripathi, sir. Hello.
Hi, sir. Am I audible?
Yes, sir. Yes, sir.
Okay. Thank you, Surinder, sir, for the introduction. And before starting, I would like to say to the audience that please be active during the session. And meanwhile, if you have any doubt, you can just unmute yourself and ask the queries. And if you're not able to unmute, then you can just put your query in the comment box. I will just answer that query and then I will move ahead. So I request all of you to make this session interactive rather than just listening and making it monotonous. So be active, and if you have any doubts or if you have any queries in between the session, you can just raise your hand. You can just ask me. You don't need to wait for the end of the session. Might be possible at the end you may just forget about the query that you have that has raised your mind. So I'm just sharing my screen. Okay, is my screen visible and I am audible properly?
Yes, sir. Yes, sir.
Okay. So meanwhile, if there is any problem in the screen or in the audio, just you can just message me or just call me on my mobile. So okay, a very good evening again to all of you. I will just start this session by this simple question that A, B, C, D. These are the three or four images. So how many images in this are real and how many images are AI generated you may think of, or the not real one which has been captured by the camera. So you can just meanwhile you can just if you want to answer anything or if you want to just have just query, you can just write comment. Okay, any answers from your side? How many images from these four you think that are real, and which one from A, B, C, D you think that is AI generated? Or deep fake, that might say. Yeah, someone has answered two images are all are deep fake. Yeah, that's good. That's good. So all these images A, B, C, and D, all these images are AI generated, and these images no doubt seems very real. At the first sight, if you don't have any proper background of what AI can do uh, with the image or video generation, then might be possible I may be confused that these images are real. But as a matter of fact, all these images A, B, C, D are AI generated. This is the power of generative AI nowadays. You can see how realistic images AI is able to just produce. So these all images are some of the celebrities, belongs to some of the celebrities. So the answer is no doubt none of these. Now, not only this, whatever we have just listened about the generative AI, that generative AI is used to generate the text or audio or video or images. And not only this, we have lots of more application nowadays using the generative AI. Let us see few more applications of generative AI. What generative AI can do, other popular actions that can be performed on image. So basically, in this session, I will be more focused on image rather than text. And no doubt, as a matter of fact, generative AI can equally be used for the text data as well. And especially, I will talk about generative adversarial network in this session. So GANs are not only the models which can be used to generate some data. We have many more models like diffusion models and others that you will learn in upcoming sessions that are also quite popular nowadays for generating the data. That may be text or that may be video or image or audio. So this is also one of the popular application of generative adversarial network. For example, I have the source image. I can use the generative model such as GAN for changing the gender of any particular image. So for example, I have just converted this image from female to male. And not only this, in the second image, you can see that what I did, we have just formed some facial hair, some manipulated this image, and we have put some beard on the face of this particular image. And the color of the hair is also changed up to some extent. Here we have just changed the pose of this particular image. In this image, he was looking in some different direction, and in this particular image, he's looking in different direction. Again, I have just changed the light of this image a little bit more as compared to this one. Again, I have just reduced the age of this particular person. To see the power of generative adversarial networks that are called GANs, nowadays it can be used for a number of purposes. Looking at one more application. So for example, I have this source image. I have just increased the age. This is called age transformation. That might be possible. You may have seen this application in the Facebook, that how will you look like in your 60s, in your 70s, or how will you look like after 10 or 20 years. Also, we have changed this image, as well as we have also put some style on it. He's wearing now glasses. Again, what we have done, we have just changed the gender of this particular image. So we just look at the different applications of generative adversarial networks, that they can not be only used for the generation of the duplicate images, rather they have different applications. It can be used for style transferring, it can be used for generating similar images, it can be used for changing the genders, and as well as scans can be used for increasing or decreasing the age of some person, that how will you look like. Yeah, it is deriving, yes, it is deriving the style. It may be anything. It is not always necessary. For example, that you have to change a style in particular way. Might be possible. We have certain kind of GANs nowadays that you may copy the style from some different image, and you may copy the face from some different image. So might be possible we have two source images, source 1 and source 2. You may copy the style of source 2, and you may copy the face of source 1, and you may generate some new kind of image. We have plenty of hybrid applications using the generative adversarial networks that will also cover in the application part. I will discuss some of the recently introduced GANs and their applications in the real world. Now coming to some more applications, it can also be used for increasing the quality of the image. For example, this is a hazed image. What we can do, we can perform image dehazing. We can perform image dehazing and we can get some clear image. So this is also one of the very popular research application of the generative adversarial network. So for example, if you are doing some kind of video surveillance or you are capturing the images of some marriage, and at that moment, the weather is not in your favor. Might be possible there is a lot of haze, there is a lot of fog, or might be possible it started raining. So in that scenario, the original images that you will capture, no doubt, they will not be quite clear. They will be blurred. They may be hazed. What you can do, you can use the generative adversarial networks to generate the similar images and removing the background. So in the same case, what we have generated a similar kind of image with different background. We have just removed the haze from this particular background. So this is one of the very popular application of the generative adversarial networks nowadays. So anything, if we talk about the artificial intelligence and deep learning models, we have lots of application. It depends upon you how you want to use particular research. So for example, if I'm talking about generative AI, it have its positive as well as it has its negative impacts. So no doubt nowadays, what some people are using, some people are also using the generative adversarial models unethically. They are using it for the fraud. So might be possible someone is just making a video, a very fake video using the generative adversarial networks. And they may use that video for making some false political agenda, or might be possible they may use that particular video to threaten you. So there are lots of cyber frauds are also going on using the generative AI. And moreover, generative AI is also helping us a lot. For example, in some good kind of applications, some ethical applications like generating such kind of images. And moreover, we can also use generative adversarial networks for the data augmentation. This is also one of the very popular application of the generative adversarial network, that we can use it for the data augmentation. So what do you mean by data augmentation? So for example, I have some classification problem and I have 2000 images for class 1 and I have 500 images for class 2. So no doubt the class 2 is minority class. Why it is minority class? Because these we have less training samples for the class 2. So what we'll do, if we'll train a model using this data, might be possible that model may be biased towards class 1, because we have given less samples of class 2 to train our model. It is similar like the case. For example, I'm giving you very simple real world example. For example, you have a kid of 1 or 2 years, and you are training him that this is the dog and this is the cat, and you are showing just 2 images of the dog and 100 images of the cat. So kid, in order to train him that this is the dog and this is the cat, so might be possible in future, if some small dog is coming with color similar to that of cat, your child may say that this is a cat. So this is quite obvious case. Might be possible you have shown 2 dogs and which are large in size. So whenever a dog of small size or puppy will come, your kid may say that this is the cat, because he have seen hundreds of examples of cat, but only two examples of 2 samples of the dog. So it might be possible he's biased or she's biased for that particular. So what we can do, how we can use generative adversarial networks in that to reduce this minority issue, class imbalance problem. We can just we can just generate some images of class C2 using generative adversarial network. We can just upsample it and we can just increase the size from 500 to 2000. So we have equal number of images for the class C1 and class C2. So one of the traditional approach for the data augmentation was that we used to rotate those images. We used to just increase the size by just resizing those images, just by increasing the brightness or contrast. So these are traditional or conventional data augmentation methods. But what was the problem with those particular methods? If you are just rotating the image, for example, I have this image 1 and I have just rotated and I have got this image 2. I have rotated it by 90 degrees. What will happen? No doubt, we have got the another image, but the features, the deep features of that particular images are not going to be changed after if you want to just rotate it. So the purpose might be not be solved for the complex problems. So in that case, what we may do, we may just generate some synthetic images using the generative adversarial networks, and no doubt we can just remove this class imbalance problem. This is another very popular application of the generative adversarial networks nowadays. We can use this scan model for the image captioning, for the scene description. For example, this is the image, and I want to describe this image. I want to just have some AI method which can be used to automatically describe some particular image. Then we can use this generative adversarial network. So, for example, it is saying that this cow is standing in a field next to house. A cow is standing in a field with house. A cow is standing in a field of grass. So these are not human generated captions, rather these are the AI generated captions by looking into the image. And these, if I see, these are the human generated captions, no doubt. This is also one of the very popular application of the GAN, and we can see the beauty and power of the generative adversarial networks, that how powerful are these generative adversarial networks nowadays. Now coming to the details of the generative adversarial networks, that is called GAN, that how they work and how they perform the task, how they are used to generate the images which look very similar to that of original image. So what are generative adversarial networks? No doubt these are the deep learning architectures used for generating the data, realistic data like image, music, or text. It may be used to generate any kind of data that mimics the target distribution. That means it is going to mimic or copy similar features to that of original data. And how they used to copy it, I will just tell you in the upcoming slides. And this GAN was basically introduced by Goodfellow, Ian Goodfellow, in 2014. And after this paper in 2014, that is called generative adversarial networks, the revolution came around in the field of generative AI. And no doubt plenty of generative adversarial networks model have been introduced in the literature. And after that, we have diffusion models and many more, which are used for generating the data. What I have told, what is GAN? GAN is a deep learning architecture. And this deep learning architecture, and I am just expecting that you have basic knowledge of deep learning, because we have already learned about the deep learning architectures, autoencoders, decoders, probability distribution in the previous sessions. I was just looking for the schedule. I'm expecting that you have the basic knowledge. All of you have the basic knowledge of the neural networks and probability distribution and autoencoders and all. So basically, this is a deep learning architecture, and it has two major components. I'll keep on repeating the things again and again, so that at the end of the session, you have the complete knowledge of the generative adversarial network in your mind. So basically, this is a deep learning architecture which is having two major components. One is generator and one is discriminator. So these are the two basic building blocks. Two basic building blocks. Entire architecture, entire success story of this network depends upon the G, generator G, and discriminator D. So in the upcoming slides, might be possible I may be using the shortcut that is called G. G stands for the generator and D stands for the discriminator. And what is D and what is G? These are nothing, but these are also some neural networks. These are also some neural networks. So you can just assume that we have two separate neural networks. We have two separate neural network architecture. One network architecture is called as Z, and one network architecture is called as D. So I hope that at this point we are quite clear that what are GANs? GANs are the generative adversarial networks which are used to generate the data which is very, very close to the real one. These are used to generate the synthetic data or fake data, you can say that. And generative adversarial networks or GANs are a deep learning architecture, and they have two networks. One is called as generator G and one is called as discriminator D. G and D both are the networks, or you can say both are the neural networks. And now why we need two neural networks in this? If I talk about GAN, GAN is made from G and D. Z is called generator, D is called discriminator. Z and D both are neural network. Why we need two neural network? Because we have different objectives. What are those different objectives? Generator G tries to create the fake data that looks real. And if generator D is generating or creating the is able to generate the fake data, then might be possible. Then what is the need of discriminator? Because what I have told that generators are used to create the fake data, which is very, very close to the real one. And no doubt, if generators are able to generate the fake data, then what is the need of the discriminator? Let us see what is the need of discriminator. Discriminator tries to distinguish between the real and the fake data, or the data which has been generated by Z. You can say that discriminator. Who is discriminator? Discriminator is a supervisor. Discriminator is a supervisor network. It is going to guide the generator, or it is going to tell the generator that this data has been generated by you, or this one is the real data. So the work of the discriminator is to discriminate between real and the fake data. So what D will do? D is going to discriminate between real and fake data. I will just keep on repeating the things again and again and again. So you don't have to worry. You have to just listen, and if any query is coming to your mind, just ask me at the moment. So what I told you, the discriminator G, discriminator D tries to distinguish between the real and the fake data. That means this is a classification network. This is a simple classification network. Whereas generator G, this is a generative network. It used to generate the data, whereas D is used to classify the data, that whether this data is real or this data is fake. So what will be the story? How they are going to work? No doubt they are basically, why this is called adversarial, because these generator and discriminator networks are conflicting with each other. Generator G will generate, discriminator will say, yeah, this is real or this is fake. And if discriminator is able to discriminate that this is the fake or generated data, or this is not real one, that means generator is not able to do his job properly. So it has to retrain and rethink. So it is playing some kind of role of supervisor. For example, you are the student, you have done some job, and you are going to your supervisor, you are showing it. Supervisor is saying that, yeah, this is not the good one. Then you have to again go back, again retest your model, again perform your work again go to the supervisor and show him that, yeah, whether it is good or not. Again, he is going to give you feedback. On the basis of that, you are going to improve yourself. So let us see how the things will go on and how that particular fake data will be generated. What is the meaning of adversarial? Adversarial means conflict opposition. Because this is called generative, means it is going to generate the data. Adversarial network. Network means because it is a deep network. So why it is called adversarial? Because generator and discriminator, this G and D, have the adverse or opposite objective. They will try to compete with each other. Generator will try to fool the discriminator. Z will try to fool the discriminator. And if G is able to fool the discriminator, that means G is successful. And when G is successful, that means if the data generated by G is not distinguishable by the discriminator. At any moment of time, if D is not able to discriminate that whether it is real or generated by G, that means generator is successful and its job is done. Now, what is the objective of generator is to fool the discriminator. Means generator will try that discriminator should not be able to differentiate between the real and generated image. So this is the objective of the generator. And what is the objective of the discriminator? Discriminator will try to always distinguish between the real and fake data. So what is the objective of this discriminator? To discriminate between real and fake data. So if discriminator is always able to discriminate or bifurcate or classify the real and fake data which has been generated by G, so that means discriminator is successful. So both have contradictory objective. This is the reason it is called as adversarial network. Both have the objectives in a contradictory fashion. So this is the reason I have written that these networks are trained in adversarial manner. And how the training is performed, what is the loss, how the things will be performed, that we'll discuss in much detail, no doubt. So again, coming to the point, discriminative model, it is one that discriminates between the two classes of the data. It is a classification model that I have already discussed. Generative, what is this generative model? Generative model G is trained on data X sampled from some true distribution D. The one which, given some standard distribution Z, produces a distribution D dash which is close to D according to some closeness matrix. No doubt this is technical one. Now I am going to just explain this in a very simple language. So what we have to basically do? This is a generator network G. I told you that we have two networks, Z and D. G is a generator network and D is a discriminator network. So what is the objective of G? I am going to just explain this technically. For example, I have this generator G. This is a neural network. What it is going to do? It will take input some random data. And what is this random data? This is called noise. Noise means it is not information, that is a pure random data. So from where I will start? I will just, from where generator will start to generate the images. Generator will start to generate the images with pure noise. Noise means without any information. It is not going to take any inputs from the real data. It is going to start from noise. What is this noise? We can say that this noise is Z. And I may use this as a Gaussian distribution. So noise is taken as a Gaussian distribution. Z is some normal or Gaussian distribution. So for example, I have taken it by giving input parameter as 0 and 1. So 0 means this is the mean of the data. So for example, you want to generate some data. Why we take it from 0 to 1? Because the pixel intensity of the image is from 0 to 255, no doubt. But generally, we used to normalize it. We used to scale it in the range of 0 and 1 for the simplicity. So I have generated some noise from 0 to 1. where 0 is the mean of that particular numbers that I have generated and 1 is the standard deviation. So this is basically, you can say, this is called Gaussian or normal distribution. So if you have given 0 or 1 as an input to your Python library, what it is going to do, it is going to generate some numbers, and the mean of those numbers will be around 0, and the standard deviation in between the numbers will be of 1, because we are generating the data in between the 0 and 1 or in some particular scale. So Z is a random numbers. G are some random probability distribution. You can say that probability distribution again means we are taking the data or numbers from 0 to 1. The probability where value basically ranges in the in 0 and between 0 and 1. This is some random probability distribution. Later Z is going to take this random probability distribution Z, and it is going to convert this form, that is called Z of Z. So what is Z? This Z, small z, this is some input sample, some instance of the data, some instance of the noise which generator has taken as an input, and now this generator has converted it has processed this data and converted this Z to Z of Z, processed it, and now these are the transformed data. So what generator has done, generator has transformed this probability distribution, random probability distribution, from one form to another form, from one form to another form. What is its target? Its target is that I want to make this probability distribution which is very, very close to actual probability distribution. And what is actual probability distribution? Just assume that this is the actual probability distribution. This is called D. And from where this actual probability distribution came from? From the input data. For example, you have taken some input data of the celebrities. You want to generate the input data of the celebrities. So this is your real data. This real data is called X, and Z is called the random generated noise. So there are two terms. X is the real data. Z is the random data, that is called noise. D is the capital D is the real data distribution. This is the probability distribution of the actual data. D is the probability distribution of the actual data, and D dash is the probability distribution of the fake data. This is the probability distribution of the fake data. So what is the objective of the generator? The generator wants to mimic this actual data and wants to train our model in such a way that it is able to generate the probability distribution D dash, which is very, very close to D. That means the probability distribution of the fake data should be as close as possible to the probability distribution of the real data. So my objective is D as close as possible to D dash. D is the probability distribution of the real data, and D dash is the probability distribution of the fake or generated data. I would definitely like to hear from you that so far, do you have any doubts? Are you clear with what I have told you so far? That what is the so far what I have told you? What is the objective of the generator? What generator wants? Generator will take input as the random noise. It is to produce the probability distribution D dash that is very, very close to that of D. D means the real data, probability distribution of the real data. So far, do you have any doubts? Are you clear with things? Anyone can just comment and answer me so that I can go ahead. Okay, clear. That's good. Moving ahead. Now I am just briefing you the overall architecture again. What I have told you. If you are listening it for the first time, if you are going through the GAN for the very first time, no doubt, just keep on listening. I'm going to repeat the things again and again. And definitely, I am quite sure that at the end of session, you will be quite clear with the concept of GAN. I hope so. Now, looking about the overall flow of the GAN, how it works. I have some real data, that is X. I have some random noise, that is called Z. So I am taking the terms X as the real data, Z as the noise that I have randomly generated using Gaussian function. I have this discriminator network. What is this discriminator network? This is again a neural network. It may be any network. It may be a simple multi-layer perceptron, or it may be some DCN, deep convolution network, or it may be a transformer network, or anything. In the vanilla GAN, that means in the basic GAN that has been introduced by the Ian Goodfellow. So this discriminator and the generator network, so both are MLP, multi-layer perceptron network. So these are the basic MLP, multi-layer perceptron network, but it is not bounded. You may use any kind of network, and I will tell you at the end that for your research purpose, what are the possible applications, what are the possible networks that you can use as a generator or as a discriminator, no doubt. This is the real data and this is the noise. What generator will do? Generator is going to generate some fake probability distribution, and this is the real probability real input sample, that is called X, and this is Z of Z, that is fake sample that has been generated by generator network Z. So generator network should also be fed with real data for generation. This is a very, very good question, and the answer is no. We are not going to give generator real data samples at this moment. Why it is so? Because I want that my generator network should learn from very scratch. Otherwise, your generator network is not going to be robust enough. If you are giving real data samples to the generator, that means we are giving the generator cooked food, ready-made food. It is going to eat and happy. And in future, that particular model is not going to be robust. It is going to generate similar kind of images. And this is not going to be very, very trained one. So it is similar like that. I am just giving you one example. So for example, if you are a cricket player and you are playing or you are training yourself on the same pitch throughout your life, then whenever you will go in the foreign or Australia or England, you are not going to get, have the success, because you are not robust enough. So we are not going to feed the real images to the generator network. It is going to train itself from the very, very scratch. It is going to train from the noise, and from noise it is going to train itself to generate images. And in the later slides we'll also get this. So generator network, it has taken random noise, and no doubt in the initial stages, in the initial epochs of the training, generator will get lots of unsuccess. Discriminator will clearly say that no, it is a fake data. Generator will retrain itself. Again, discriminator failed. Again, generator will generate new data. Discriminator will classify it. Generator fail. Got it? So it is something like, again, I am giving example. For example, you are doing some PhD in your under your supervisor. Your supervisor is giving you ready-made problem and ready-made model that just run it and give me the result. Might it be possible you are able to publish your first paper in few months, but in future you will be a failed researcher. So this is the reason what supervisor will tell. It is going you. He's going to just tell you, just go and learn about the mathematics of the deep learning. Just go and learn this. Just go and learn that. Feedback loop is not shown here. That I will show. I have multiple figures. This is one of the very basic figure. In the upcoming slides, I will show you the feedback kind of thing. Got it? So it basically starts from very scratch. I think you have got the point. Now, what GAN model trained only on one data set and can be is the GAN model trained on the one data? It depends upon the type of the problem. GAN data set might be possible have different kind of samples, different types. So, for example, if I'm talking about the celebrity data set, it has the samples of, it has the faces of hundreds of celebrities. So in that case, you have to give quite rich training data samples. It is going to learn the entire probability distribution, and no doubt in future it will be able to generate multiple type of faces. So it depends upon which kind of data you are giving. If you are just feeding the photo of, for example, Narendra Modi or Rahul Gandhi or some political figure. So if you are giving only one type of images, no doubt your GAN model will be able to generate only that particular kind of images. But if you are providing 5 times or 10 times of images, 10 types of images, no doubt your model will be able to generate 10 types of images. We will also see that in the upcoming slides. So discriminator, what discriminator will do? Discriminator is going to just differentiate between the real and the fake, and on the basis of that, loss will be calculated. And no doubt, if the discriminator is able to generate, if the discriminator is able to differentiate between 0 and 1, 0 for the fake and 1 for the real, that means discriminator loss will be less and generator loss will be more. And if the generator is not able to classify correctly between the real and fake images, then in that case, discriminator loss will be more and generator loss will be less. Got it? Let us move ahead. I will show you more architectures and more details. I'm going slowly and step by step. Overall, I'm just revising the overall idea that we have discussed so far. We have a generator network G that generates the fact sample and tries to fool the discriminator. We have discriminator network D, which tries to distinguish between the real and the fake samples. We have to train them against each other. Why? Because the objectives are contradictory. Discriminator generator will try to fool discriminator D, and discriminator D will try to just classify or segregate that these are the generated images or these are the real images. So the objectives are contradictory. So that's why they are trained against each other. So we have to repeat this training to and fro in order to have the robust generator G and robust discriminator D. So no doubt the objectives are contradictory, but in order to have a good GAN, you should have a robust generator G as well as a robust discriminator D. So both models or both networks should be robust. Otherwise, your overall GAN model will not be good. And what is the reason for it? That I will also tell you. Now, moving ahead. Again, this is the real world images. What is this small x? Small x is the sample that has been taken from the capital X. This is the real sample, and this Z is the noise, and this is the generator network. Again, this is neural network. This is a neural network. This is a neural network. Robustness of discriminator is achieved by, robustness of discriminator is achieved by training generator network. In the later on epochs, generator will be able to generate quite realistic images. And in that case, discriminator, it will be very hard for discriminator to discriminate between the real and the fake images. So no doubt it is going to get hard samples from the generator. And in order to discriminate between the real and fake, it has to again it has to change its weights and biases and make himself strong so that it can be able to bifurcate between the real and the fake images. So what I said, I have a batter, I have a bowler. So what batsman will try to do? Batsman will try to give a 6 to the bowler. then bowler will also try to give a good ball so that batsman cannot hit. But ultimately, no doubt, the goal of the batsman is to hit the sixes. But if the bowler is weak, then in that case, batsman will not be a good batsman in the future, because it needs a quite competitive bowler so that it can have the hard training. Okay. So basically what discriminator will do, discriminator is going to just discriminate between the real and fake, and on the basis of that, discriminator is going to just have some kind of loss. So what discriminator will get as an input, discriminator will get two types of inputs. One input is X. So discriminator will produce some probability distribution value from 0 to 1. It will take real data sample. It is going to generate the value from 0 to 1. 1 means real and 0 means fake. And this is input 1, input type 1. And what is input 2? Input type 2. Input type 2 is that discriminator is going to get Z of Z. That means this is the generated data. And again, it has to give some probability distribution between 0 to 1. And can anyone tell me that what should be the value of Z of Z and what should be the value of D of X? This time I am telling you, in future I will again ask you the same question. The value of D of X should be near to 1 because this is a real data sample. So what label I have given? I have given label 1 for the real sample. I have given label 0 for the fake samples. So the value of D of X should be close to 1 so that it can clearly say that this is the real sample, and the value of D of Z should be equal to 0 so that I can clearly say that it is a fake sample. And if the value of this probability value is 0.5, that means discriminator is confused that this is real or fake, and no doubt it will not able to respond properly. Again, coming to one more point, I'm going in a little bit more detail. That I said that you have to generator will start from the random noise. So for example, this is the random noise. So just look at this circle that I have drawn. Z is equal to this. This is a vector. I have just drawn a vector of 100. That means I have just generated 100 random samples, 100 random data points. So the mean is 0. That's why some points are like this, less than 0, and some points are more than 0. So overall mean is 0, and the standard deviation in the days of 1. So this is a 100 cross 1. What I will do, because we have to generate the image, so I need to just reshape it. So just reshape layer. What reshape layer will do? Reshape layer is going to just reshape layer is from 8,8,128. So what is going to reshape layer? And before reshape layer, there will be a dense layer. Dense layer is also called as fully connected layer. It is going to upsample data, and after that we are going to reshape it, and we will generate the samples of 8 cross 8 cross 128. That means we have a 128 feature of size 8 cross 8. Got it? So after that we have a convolution 2D transpose. This is the what I am telling you now. How to generate some image from the noise. Details of the technical details of generating the image from the noise. What I did, I have generated 100 numbers, upsampled using the dense layer, and reshaped it to 8 cross 8 cross 128. Again, I have used convolution 2D transpose. It is used to again upsample it. Again, I have upsampled this to 16 cross 256. Again, I have upsampled it using the convolution 2D transpose 32 cross 128. Again, I have applied convolution 2D transpose to this, again this, again this. So that means at the last I have created the data in the form of 64 cross 64 cross 3. Why it is 3? Because I am making RGB image. in order to make it RGB, I'm just making it RGB. So I have a 64 cross 64 matrix along with three channels that is called as R, G, and B. So ultimately, we will have a 64 cross 64 image with three channels that is called as RGB. It depends upon what dimension of image you want to take. Now let's understand the same thing with the help of some examples. So for example, I have some MNIST data set. So MNIST is a fashion data set where we have some images of coat, pants, shirts, and all the and trousers, all the things. What I told, what will be the overall process? The overall process is going to be like this. I will take some sample, some data sample that is called X. It is the real data sample. And for example, at any moment of time, this is my generator network Z. It is it has generated some fake sample. Now this is the real one, for example, and this is the fake one. Just assume it. And now we are going to give our discriminator D. This is the discriminator network D, and I am going to give to the discriminator that this is the real sample X and its label is 1, and this is the fake sample Z of Z and its label is 0. Now you need to discriminate. No doubt in the training phase, I am not going to just give the samples. Discriminator model has to just generate the label. So now what will happen? This discriminator is going to just process this data and produce an output value that is called D. And this D will be from 0 to 1. And if this D is close to 1, we will say that this is the real image. And if this is close to 0, it is going to say that this is the fake image. So this is the overall process. Now, coming more into the details of training the generator and the discriminator, I have this noise vector. This is some artificial instance which has been generated by the generator. So noise will look like this in the initial epochs. So at the end of this session, I will also show you some code. So in the initial epochs, generator is going to generate this kind of image. Why it is so? Because this is a pure noise. Generator is going to start with pure noise, that is called Z. So your image will look like this because this is total random numbers, and these are the real instances. Discriminator has to discriminate between the real and fake. So at the initial epochs, the job of discriminator will be very, very easy. Why it is so? Because in the initial epochs, generator is going to generate the samples which are very, very close to the noise. And discriminator is going to clearly bifurcate that this is the real or this is the fake one. Right. Now the point is that while training the discriminator, I will again tell you this in detail. While training the discriminator, generator is constant. We cannot train both the generator and discriminator network at the same time. It is the discriminator only trained on the yes. Discriminator will be trained on the both type of data. It is called real data and fake data. Because generator is discriminator. Discriminator is trained on both type of data, that is called real data and fake data. Why it is so? Because discriminator is a classification model. It needs to know about the real and the fake data. Then only it can train itself and decide that which one is real or which one is fake. But if I talk about the generator network, we are not going to give input of real data to the generator. So this is the real data. I'm not going to just input this real data to the generator. Why it is so? Because then it is going to copy the probability distribution from the real data. Got the point? So we are not going to do this. And if we are generating the similar images, we are not just copying and paste it. So one of the ways that you just copy the images and paste it, you will get the similar images. We are not making the exact copy, we are making the similar copy. So I am not going to give generator the real samples, otherwise it is going to be biased one. It is going to just mimic that distribution, and it is going to just fool that discriminator very easily. And if it is going to fool the discriminator very easily, in future it is not going to generate quite good examples. Got it? So what generator will do, generator is going to produce this noise data, and it is going to just give this discriminator, and discriminator is going to just discriminate, and after that it will get some feedback that whether I am able to fool the discriminator or not. And if it is not going to fool, if discriminator is not fooled by the generator, then it has to retrain itself, produce different probability distribution like this. Again, coming to the same point, this is the more clear picture. What I told you, that this is the training of the discriminator. Look at the heading. This is the training of discriminator. While training the discriminator, generator is locked. That means I have trained generator up to some epoch. For example, I have just trained my generator for the 500 iterations. Then I'm going to lock it. Now I'm going to test discriminator. Generator is generating some images. Discriminator is getting inputs from two sides. This is a very important point I am again telling you. Discriminator is getting input from the two sides. One is the real data sample X, and one is the generated data sample, and generated from where? Generated from the noise, and this X is real. So discriminator is getting two kinds of data, and it is going to classify that which one is real and which one is fake. And after the classification, we are going to calculate the loss. And I will also discuss in detail about the loss function. Can you explain the locking again? Yeah. Again, I'm telling you. What I told you, that generator and discriminator are not trained at the same time. What we are going to do, we will train generator first and we'll lock it. For example, I have trained generator for the 500 epoch, and then I will lock it. What I will do then I will test my discriminator. I have made my bowler strong, and then I will test my batsman. So I want to make my team strong. That's why first separately I trained my bowler quite well, and now I will test my batsman. It is something like that. And after that, I will train my batsman well, and now I will check my bowler, that how robust it is. Both need to be strong. So what I will do, I have trained my generator, and now I logged it. Now I am going to further. What is the generator? What is the generator train? This confusion is quite obvious. First of all, generator will generate the images from the noise, and it is going to give. So, for example, I have some prefix discriminator. Got it? Generator is generating images from the noise and giving to the discriminator. Discriminator is able to classify itself. Again, it is going to propagate, back propagate, update its weight, give to the discriminator. Again propagate. Both are the network. What I will do, first I will train my generator up to some extent. Then I will train my discriminator up to some extent. I will train my generator up to some extent, and I will train my discriminator up to some extent. Vice versa. For example, I need to make a team. I have a bowler, I have a batsman. Both are untrained. I will say my bowler to, I'm going to train my batsman. I will say my bowler to bowl him. Bowler will do something, and batsman is going to do something. Again, batsman will get some training. Again, I will check. Go to train my bowler. Now do it hard. Bowler will give some tough competition to the batsman. Again, I am going to train batsman. Batsman is going to give a tough competition to the bowler. So I will train one by one, because I need to make my generator and discriminator both strong. So naturally, at the very beginning, generator model is going to be quite loose, because it is going to generate the images which are very, very noisy. Good to see. Discriminator will be good. because it will be able to clearly discriminate between the probability distribution of the real and the fake data, because the probability distribution of the real and the fake, the feature map is very different. So at the initial stage, the job of the discriminator will be very easy. So discriminator will clearly discriminate. Now generator will start train itself, make the probability distribution close to this original, that is called D. After some epochs, I will show in my next slide that how this Z will be trained to give a good competition to the discriminator. In the initial phase, no doubt, the discriminator will be robust. Why it is so? Because the job of the classification will be quite easy for the discriminator, because the data distribution is very different. Got the point? Have you got the point? Yeah. So no doubt at the initial stage, discriminator will be quite good, because why it is so? Because the generated samples will be very close to the noise, and at the later stage, it will give generator will give tough competition to the discriminator, and discriminator has to change itself. Now what will happen? This will be the loss, and discriminator is going to train itself again. It is going to train itself. After that, this is the turn of the generator. Again, I am going to fix it. I have fixed my discriminator. What will happen? Discriminator will get data X from here and Z of Z from here. So it is going to form classification. I will have some loss. I will back propagate. Again, I will generate images, loss, back propagate, generate, loss, back propagate, and like this. So this is the reason I said that ZAN. A means adversarial. This is the meaning of adversarial. I will train generator and discriminator in to and fro manner. By the course of iterations, both Z and D will make itself strong and robust enough to give a tough competition to each other. Now let us see. Again, I am telling you the same thing in detail, for which might be possible you have some confusion. So, for example, I have some discriminator D, discriminator network that is called D. I'm just changing the ink color, make it blue. Yeah. So for example, I have some discriminator network D, and the job of the discriminator is to classify the data between 0 and 1. So initially, what I told you that this is some random probability distribution, and the shape of probability distribution is this, like this. And this is real probability distribution. This is real probability distribution. What is this? This is real probability distribution. So the label of this probability distribution is 0, and the label for this is y equal to 0. Label for this is 1. So what generator G will try to do, it is going to take input as data samples of Z, and now what it is going to convert, generator Z is going to convert this Z into Z of Z. It has transformed this noise data in this form, and now it is give this input to the discriminator. Discriminator is going to just classify, and at the initial phase it is quite assumed that discriminator is going to easily classify that this is the fake samples and this is the real sample. So it is going to calculate the loss. On the basis of that, generator G is going to change its weights and biases, W and B, and now it is going to just take these input samples and convert these input samples. These are the transformed input samples, and again convert this in this form, Z of Z, this form. So the probability distribution, it has, and the first 10 epochs, this is 10 epochs, this is output after 100 epoch, this is after 1000, and this is after 5000 epochs. So after 10 epochs, it is able to convert this probability distribution from this to this, and after 100 epochs, this probability distribution has changed from this to this. Again, it is going to give input that take this Z of Z dash and give me the and just classify that whether these are the real or fake. again discriminator D will say that, yeah, whatever the data you have generated is fake. I'm able to clearly classify. Now again, this generator is going to update its weight and biases, and now it is able to just convert this probability distribution G dash into Z dash dash, for example. So now why I have drawn this shape? These shapes are not random. I am just trying to show you that the probability distribution shape by the course of iteration will become nearer to this one. This is the actual. So circle is the actual probability distribution, and this amoeba like shape is the pure random probability distribution. And now you can see that this pure random probability distribution is taking the shape, and it is mimicking the original distribution that is called X. Now after 1000 epochs, its shape is something like this. Again, it is going to give input. Now check. Now it will be a little bit difficult for the discriminator D to classify. So might be possible after 1000 epochs, discriminator will again, generator will be locked, and discriminator will be further trained on the real and the fake images. It is going to train itself to bifurcate between the data distribution that is called Z dash dash and X, and again it is going to train itself. After that, it will become more robust, give more hard competition to the generator. And after 5000 number of epochs, you can we can see that this probability distribution that has been generated by the generator network Z is very close to this one that is called real. So in the initial, what I told you, this is D dash and this is D. D is the actual probability distribution. D dash is the generated probability distribution, and my aim is to make D dash close to D so that discriminators would not be able to discriminate between X, Z of Z, that is data generated from the noise. Training is performed in the backend. If you have any doubt, just ask me or just and even from the input. Am I audible now?
Little bit voice is breaking, sir.
Little bit voice is breaking.
Now it is fine, sir.
Okay. So so can anyone just tell me, so far you have got the point that how basically the training of generator and discriminators is performed in the backend? Any doubt in this particular slide? In this slide, I have just discussed in detail by the course of iterations how generator Z is updating itself to give a competition to the discriminator and generate the images which are very close to the real one. Have you got this point? Should I go ahead? Discriminator training is with real from the real data set. Actually, that comment has flashed back. Just give your comment again because it has flashed back. Okay, let me check that particular comment. Check. The discriminator training is with the real from the data set and fake from the generator. Is this correct? Discriminator is training with the real samples from the actual data set and fake samples from the generator. Yes, you are correct. Yes, definitely you are correct. Discriminator D is getting the samples, real samples from the original data sample and fake from the generated samples. Yeah, this is correct. Now moving ahead, so these are the for example, this is the real total distribution. This is the data total distribution. This is the real total distribution. Now what discriminator will do? Discriminator will discriminator D will be trained on the data. Now will be is P data is real distribution of Z, that is data that has been generated by the discriminator. This is the fake. So after the taking, what will happen will be from these dots from the X and few dots from the of Z. So it will get these samples from both the sides, and after training, what will happen? It will become D of X theta. That means this is called parameterized network. That means D of X is, this means D of X is parameterized with theta. Now this is a trained discriminator model, trained from both from the fake data and from the real data. And now what will generator is going to do? The trained generator Z. So before that, I just explained to you about the training of generator and discriminator. Now I am just giving you the visuals of the trained generator and discriminator model. I have now a trained generator Z that is parameterized by theta. That means during the training, I have just updated the weights and biases. And now this P of Zx is the probability distribution of the generated data. This is the probability distribution of the generated data, and this is the probability distribution of the real data. So this is the probability distribution of the real data, and both D and Z are the differentiable functions. Why it is so? I will tell you later, because we are going to just we are willing to get the maxima or minima of the loss. So definitely, if the functions are differentiable, then we will be able to get the maxima or minima. Now coming to the loss function, now I think you have got the overview of the generator and discriminator. Now I am digging a little bit in detail, and I will tell you about the loss function, that how the loss is calculated and what is the loss function for the generator and what is the loss function of the discriminator. And after learning the loss function, we will be able to clearly get the intuition behind the objective of the generator and the discriminator. So this is a very popular loss function that is called as cross entropy loss. This is a very popular loss function that is called as cross entropy loss. So what is this cross entropy loss? I think I should hide it. Hide meeting controls. Yeah. So what is this cross entropy loss? Let me change the colors so that you can differentiate it clearly. Yeah. This is called cross entropy, binary cross entropy loss. L of y hat comma y is equal to y log y hat plus 1 minus y log 1 minus y hat. So y is the real label and y hat is the generated label. Got it now? So y hat is the generated label and y is the real label. Got it? So first I will discuss the loss of the discriminator D, and after that I will discuss loss of generator G. So if I talk about discriminator, what I have told you that discriminator D is getting input from how many sources? From two sources. One is from X and one is from Z of Z. That is, one is the generated samples and one is the real data samples. It is going to get input from two sources. One is the data samples which has been generated by generator, and one is the real data samples. Got it? Okay. So first I will discuss about the labels for the data coming from PDataX, means labels from the actual data. So for that, y will be equal to 1. What will be the value of real samples? Label for the real samples, y is equal to 1. At the initial stage, I have already told you that label for the initial sample is 1 and label for the fake sample is 0. Got it? So y will be equal to 1 if the data is coming from this source, from the real sources, and y will be 0 if the data is coming from the generator. Actual label for the generator is 0 and actual label for the real data is 1. So y will be equal to 1 for the real data samples, and what will be the y hat? Y hat will be d of x. What is d of x? D of x is the probability distribution value that has been given by the discriminator. So d of x is nothing but it is the output. Okay. So putting these values in this particular equation. So first, what will be the y hat? Y hat is d of x. It may be anything. It may be any value from 0 to 1. This is the output that has been generated by the discriminator. And what is this y? Actual label? Actual label is 1. Why this actual label is 1? Because data is coming from the real samples. Got it? And this will be equal to log. If you will put the value of y equal to 1 here, so it is going to be 1 log d of x. The plus second term is 1 minus 1 log of 1 minus something. So this second term will become 0. So the final output will be log of d of x. So this is for the data coming from the original sample. Right. Now, second term is if the data is coming from the generator G, then label kya hoga? Then in that case, label y will be equal to 0 and y hat will be d of z. That means it is getting this input and it is producing this output. So in that case, I am putting the value of y is equal to 0 in this particular equation, that is called equation number 1. I am putting the value of y equal to 0. So what will happen? This will be equal to L d of z, this comma 0 equal to, if I put value of y 0 here, then the first term will become 0. This is first term, this is second term. So first term will become 0 and the second term will be 1 minus 0 log of this. So it is going to be log of 1 minus d of z. So I am labeling this as A and I am labeling this as B. So now total loss kitna hoga? What will be the total loss? Total loss will be equal to A plus B. A is this, B is this. First loss is for bifurcating the real data and second loss is for bifurcating the generated data. So the overall loss will be log of d of x plus log of 1 minus d of z. So this is A plus B. So this is the overall loss for the discriminator. You got this point? This is the crucial point. If you want to do some kind of research in the using the generative adversarial network. So this is a very, very, very crucial point. Do you have any confusion or have you got this point? because this is the only mathematics that GANs will perform behind the scenes. Clear? That's good. So this is the loss for the discriminator. Now coming to the generator, what will be the loss for the generator? So now taking of the generator, what generator wants? Generator wants to make d of z equal to what generator wants? D of z should be equal to 1. Generator wants that the label for the generated sample should be equal to 1. Whereas what discriminator wants? That d of z should be equal to 0. Because generator wants to fool it and discriminator don't want to fool. Generator wants to bifurcate the data which has been generated by the generator. Now, if I talk about the generator loss, so there are two terms in the equation that I have given, log of d of x plus log of 1 minus d of z. So we have two terms. One term is this, second term is this. So the generator do not have any role in this first point because it is totally dependent upon the discriminator. So generator will not try to optimize this first component. But if I talk about the second term, log of d of this, so what generator will try to make, generator will try that the value of this should be d of z should be equal to 1. Generator wants this. So when the value of this will become equal to 1, if I plot a graph like this one, so if the overall value of log of 1 minus d of z is very less, that is close to infinity, at this point this will become equal to 1. So ultimate game is that, and that ultimate point is that, don't go to the graph, ultimate point is that generator will try to make this value equal to 1. So if I want to make this value equal to 1, when this value will be equal to 1, this overall value will be minimum. So definitely generator G will try to find the minima of this. Is it okay? Generator G will try to minimize it. Why it is so? Because it wants that d of z should be equal to 1. So that's why it will try to minimize it. And whereas what discriminator will want, what is the choice of the discriminator? Discriminator wants that this d of x should be equal to 1. That means label for the real sample should be equal to 1, and this should be equal to z of z. This label should be equal to 0 because it is the fake data. So label should be 0, and if this is 0, then this is maximum. So in that case, discriminator D will try to maximize this, and whereas generator G will try to minimize it. So the objectives of both the generator and the discriminator is contradictory in nature. दोनों के ऑब्जेक्टिव क्या हो गए? Contradictory. क्योंकि जनरेटर चाह रहा है इसको मिनिमाइज करें, जनरेटर चाह रहा है इसको मिनिमाइज करें, एंड डिस्क्रिमिनेटर चाह रहा है इसको मैक्सिमाइज करें. Got it? No doubt if you have, because this is the mathematics. If you have any doubts, you may just I will hand over the PPT and you may just revise the concept again, and I hope that you will get it. This is not that much difficult, but at the first time you may think that it is something which is a little bit difficult for you. Anyone can I have some feedback that anyone that have got this point about the loss function? Otherwise it's okay. So now if I will pick up these equations 1 and 2, then it will be quite clear that what is the basic objective function of the overall GAN. So basic objective function of the overall GAN is that we have generator G and discriminator D, and we have loss function log of dx plus log of 1 minus d of z, and where z tries to minimize it and d tries to maximize it. So this is the equation that you will get in the that has been introduced by the Goodfellow. This is the same equation that we'll get there, that generator as discriminator tries to maximize it. This is the reason we say that it is a generative adversarial network, because the objective of both the generator and the discriminator are opposite in nature. Now moving ahead. Process and probability distribution. So for example, this is the probability distribution of the actual data, and this is the probability distribution of the generated data. This is the probability distribution of the actual data, and this is the generated data, and this is discriminator D. Then discriminator D is clearly able to bifurcate between the generated probability distribution and the actual probability distribution. It is quite easy for the discriminator to bifurcate between the actual and the generated. After some epochs, if you will see the instance B, this generator will update its probability distribution. Real data distribution is going to be same. This is real data distribution P. This is real data probability distribution, that is P of data X. So real data distribution is not going to be changed. What going to be changed is the generated probability data distribution. So for example, after few iterations, generator has it updated its probability distribution data based on the loss. So discriminator has changed itself like this. So ultimately, might be possible a discriminator is going to produce the value from 0 and 1. So discriminator had changed its classification curve and made like this. Now little bit difficult for the discriminator. After this point, again, based on the loss, this is the loss between the probability distribution of the real and the generated, that is z of x. Again, generator G has changed its probability distribution, that is called z of x. Now it is very close to that real one. Discriminator, some difficulty for the discriminator, but it is able to do it. After 5,000 epochs, for example, the probability distribution P data of x is very similar to probability distribution of generator, because both have overlapped. So if both models have overlapped, then discriminator don't have choice. Classification curve of discriminator will be like this. Now what will happen? It is going to produce values 0.5. The classification curve of this is going to be same for the discriminator and the generator. Now this discriminator is not able to discriminate between the real and the fake samples. This is the overall story of the generative adversarial network models and how they basically work. So I hope that you have got some intuition of the generative adversarial network. Now I will just give you a flashback of some applications of the generative adversarial networks, as well as some problems of the generative adversarial network. So this is some visual impact that how we used to generate images. In the initial epochs, the images are like this, and after 10 epochs, might be possible images are like this, and after 70 epochs, might be possible images are like this. They are very, very close to the real one. Now let us see what are the problems with the GAN. This is the very important point, that what are the basic problems with the generative adversarial NAND. So these are the two problems. One is called as non-convergence and one is called as mod collapse problem. These are the two very basic problems of the generative adversarial network. One is the non-convergence and one is mod collapse. What is this non-convergence problem? So generally what happens in majority of the deep learning problems, we have to either minimize or we have to either maximize. Those problems are single objective problems. But GAN problem is multi-objective. Multi-objective means this is a min-max problem. Generator tries to minimize the same loss function. At the same time, discriminator wants to maximize the same loss function. So there is a trade-off between the generator and discriminator, and it is very difficult to have the Nash equilibrium. Get the same point. For example, I have some min-max problem V of x, y. So at this stage 1, so if the value of x is greater than 0 and y is greater than 0, then v is greater than 0. Now what I did, I increased y and decreased x. Now x is less than 0. Why did GAN start generating cats in the first epoch and not other images? So that is just for an instance. You can see that might be possible they started generating cats at the initial stage. Technically, if you want to get into the detail, that is called Nash equilibrium. So initially, might be possible it have got the images which are very close to the cat one, and discriminator D was not able to discriminate between the generated and the real images. So it will try to generate same kind of images. So at the later stage, if discriminator is not able to discriminate between this generated output and the real one, then generator will try to generate similar kinds of images. That is called as vanishing gradient problem. This is called as vanishing, that I will discuss. So sometimes it happens that generally GANs start generating similar kind of images. In that case, it is not able to generate the bifurcated data or the samples from entire data set. So no doubt that's a good question. So what I said, this is very difficult to have a Nash equilibrium between the generator and the discriminator. If we see this kind of example, so this is the x and this is the y, and this is the x and y. So if we'll increase x, might be possible x, y may decrease, and if we'll increase y, might be possible 1 may decrease. So it's a multi-objective problem. So it is very difficult to have the convergence because one tries to maximize the same and one tries to minimize the same. Now coming to the mod collapse problem, and this is also answer of the question that has been asked by someone, that why did GAN start generating cats in the first epoch and not other images? So basically, for example, generator Z has generated some images, for example, like cats, and discriminator D is not able to bifurcate between the real and the fake images. So what generator will think? Generator will think that I have done a good job. I have generated a quite good sample. It will again try to generate the similar images like a cat. And again, discriminatory D is not going to bifurcate. So for example, if bowler is bowling to some batsman and he has given some short ball and batsman is out, again at the same time second batsman has also did the same job. He's out on the short ball. So he will think that short ball is quite good enough, and he will keep on sending the same kind of ball. So it is similar the case. Sometimes what happens, discriminator, if the discriminator is weak and it is not able to discriminate some particular type of data that has been generated by generator Z, then what will happen? Generator G will try to generate similar type of data samples or some subset of the samples of the data. So that is called as mod collapse problem. Got it? So this is the same example that I am telling you. So for example, this is the real data distribution, and this is the generated data sample. And if discriminator D is not able to bifurcate between the real and fake data in the initial stage, then what the generator will try to do? It will just try to generate similar kind of data, because at every attempt it is able to fool the discriminator. So it is not going to just diverse itself and try to generate same type of images like this. Here we have repeated images of some digits, or we have some repeated faces. So I think Preeti, Bosco, have you got the answer of your question? Okay, thank you. Now coming to some of the applications of generative adversarial networks. So I will be a little bit fast because I have I think 20 minutes remaining. So for example, what are the real life use cases of the generative adversarial networks? Image generation. This is one of the very popular application, that if you want to generate real images from the random noise, then we can use this. And image to image translation. So for example, we have CycleGAN. It is used to just translate some images like sketch to photo, like horse to zebra, like this. So if you want to translate one type of images to another type of images, we can have CycleGAN kind of things. Super resolution, that I already told you. If we have some blurred image, and if I want to increase the resolution of the image, then we can use SR GAN, that is called super resolution GAN. Data augmentation in healthcare, that is also one of the very important applications of the GAN. That if you want to have image augmentation, then we can generate some realistic images and augment my data. And we can also use GAN models for the text generation and enhancement. These are some types of GANs, like popular GANs like Vanilla GAN, that has been generated by Goodfellow. After that, we have conditional GAN, we have DC GAN, we have SR GAN, we have cycle GAN. And no doubt, if I talk about today's world, there are more than hundreds and hundreds of GAN that has been developed by different researchers for different purposes. So no doubt, in future you may have GAN of your type that can solve your kind of problem, because there is a free lunch theorem which says that no model can be fit for all kinds of applications. So if I talk about Vanilla GAN, basically this has been introduced by the Goodfellow in 2014. This was the starting of the GAN models, and where we should use for the educational purpose to understand the basic GANs and creating low resolution images like MNIST. And basically this Vanilla GAN model uses MLP, that is multi-layer perceptron, for the Z and D for the generator and the discriminator. Where we don't have to use for complex and high resolution image generation, we should not use this Vanilla GAN model, because it will not be able to generate real-time and complex images. For such kind of applications, you can use this Vanilla GAN, that is the basic GAN that has been introduced by the Goodfellow. Second, so basically, I already told you that if you want to have image translation kind of job, then you can use cycle GANs. So basically, this cycle can have two generators and two discriminators. So for example, I have this zebra type of images, and I want to copy the style from from some other locations. So I may just convert this image to this form and like this. So we have two generators and two discriminators, or two discriminator and one generator. We can have combinations of both. Similarly, we have conditional GANs where we can give some condition that these are the class labels, and you have to produce images like this. So if you want to control, so for example, if you want to change the gender, color or shape, you want to say to your model that you have to generate green color images or blue color images. So if you want to give any kind of control, then you can provide this class label and your model is going to perform like this. So for example, these are the labels that we have inputted, and this is going to generate like this. So for example, to you want to make this image from black and white to color, then you can just give some condition that you have to produce image like this. So you can go in details of these kinds of models. We have different kinds of generative adversarial networks. So you can use those networks for problem solving. DC-GAN. So if you want to generate some complex images like face, objects and textures, then you should not go for the vanilla GAN. You should go for the DC-GAN. What is the difference between the vanilla and DC-GAN? Vanilla GAN uses simple multi-layer perceptron as D and Z, whereas DC-GAN uses deep convolution network as discriminator and generator. So the basic difference between the vanilla GAN and DC GAN is that DC GAN uses basically deep convolution network as a generator, as a discriminator. So it is able to generate high quality or complex images. Super resolution GAN is also quite popular because majority of the real world images are not good enough. You can say that if you have the images which are blurred one and you want to have some good quality images, like in the military applications there were some satellite images, and if you want to increase the resolution of those satellite images, then what you can do, you can have the super resolution GAN, which can be used to improve the resolution of the given images. So for example, I have cropped this image and I want to increase the resolution. I may increase the resolution using SR GAN. So thank you all of you. Now I will just show you some code, and I don't have time to just perform code in front of you. What I will do, I will just use some trained model and I will show you the code and that how basically GAN models be implemented. I will share you the link of this Kaggle notebook where you can just run this code and see the output and understand the code part, that how basically it works. So is my screen visible? Is my Kaggle notebook visible to all of you? Yes, okay. So I will just run this model on the MNIST dataset. That is the digit dataset. Just go through it, and if you have any doubts, you can just ask me. So in the first cell, we have just imported some packages. So I will share this link with you, this code as well as a link with you. What you need to do before running this, you have to make your internet on. In the right hand side, you will see this internet option, and you have to just on this internet. Otherwise, you will not get the access of the GPU. So if you want to get access of the GPU, then you have to make this on, internet on. So this cell is run. Now go through this. I am loading the images into the memory. This is just for loading the MNIST dataset. I am just importing the data and making this training sample as X and Y. Now, after loading the data, I am just plotting the data so that I can just show you that which data I have loaded. So I have made a grid of 5 cross 5. You can just see this is the grid of 5 cross 5. So this MNIST data set is the data set of digits. Got it? Now after training, I just reshaped the data. Now what is the meaning of this buffer and batch size? Because we are using GPU, so if I am giving a batch size of 256, that means it is going to just make the batches of 256, groups of 256, and extract the features and process the images parallelly. So for the parallel processing, you need to make a batch size of 256 or some other size, depending upon your GPU capability. And basically, this is the buffer size. So it is going to load the images in the buffer. So it can just makes the computations faster. So this is making of generator model. So generator model initially we have to just reshape and then perform convolution 2D transpose. So if you remember in the initial slides, I have also told you that from random noise, if you want to just make an image, then you have to perform 2D transposes. So convolution 2D transpose layer is used to upsample the image. We need to upsample the image again and again in order to make the image of the desired size. So this is the generator model that I have called. I have inputted this random noise from 0 to 100, and I call this generator, and now I am running this. So after running, you can see that this is the generated image without training of the model. So this is the initially the image is pure noise. That was also one of the question that are we getting any input from the real data? No, this is a pure noise that I have generated. Random dot normal 1 comma 100. I am generating numbers from 100 numbers and making a 1D vector. Now I am just making a discriminator model. So this is the discriminator layer. So this is going to just call convert to layer, and after that it will flatten it because we have to make a probability distribution from 0 to 1. So this discriminator model is calling and you are getting an output from 0 to 1. So for example, this is getting output 0.5. This is the cross entropy loss that I have discussed, that it is going to use binary cross entropy loss. And this is the discriminator loss. What is this discriminator loss? Discriminator will get input from the real output and from the fake output. So this fake output is the data that has been generated by the generator, and this is the real data sample. So the total loss for the discriminator will be real loss plus fake loss. That I have already discussed in slide. That the loss of discriminator is A plus B, where A is the loss from the real data sample and B is the loss of the generated data samples. This is the generator loss. Generator will try to minimize the loss function. So these are checkpoints that I have already have in my model and saved some checkpoints so that I can show you the output. So I am just running for it for the 50 box, but my model is already trained and I have already saved the checkpoints so that I will be able to show you some output. So I'm calling the train function in order to train our model, and I'm saving the box after each 5 iterations. So let's check. I'm not going in each line of the code because I will give you the code, and what you need to do, you need to just if you have any doubt in the code, you need to copy it and you have to paste it in the GPT. It is going to tell you about the syntax of the lines, that what this line meant for. And I have already told you about the logic of the GAN model. So I think you will be able to clearly understand the code as well. And if I talk about the syntax, you may just get this syntax information of the syntax from GPT. So these are the images after 5 epochs. You can see that this is the MNIST data set. और ये जो images हैं वो 5 epoch के बाद है. 5 epoch के बाद आपकी images ऐसी दिख रही हैं. In our case, images after 10 epochs. After 10 epochs, images are looking like this. 20 epochs. After 20 epochs, images are looking like this. 30 epochs. After 30 epochs, images are looking like this. 40 epochs. After 40 epochs, images are little bit clear. You can clearly understand that which number is this. After 50, there is more clarity. So at the last, I have just created a GIF file that is going to show you video-like thing, that it will start from the random noise and it is going to generate some data for you. So I do hope that you have got some concepts of the generative adversarial network. And I will also give you this code, link of the code, so that you can just practice with yourself, and you can try different generator and discriminator networks. So in the initial slides, I have already told you that you may have any Z or any D. You can try even transformer models as a generator and as a discriminator, or any state-of-the-art model to generate the images of your choice. You can have your own GAN model after some hit and trials, and you can research a lot in this field. So thank you very much. At the end, I would like to have some discussion with you. If you have any question or any doubt or any query in your mind, you can just ask me.
Hello. Yes, participants, if you have any doubt, please ask, or you can write in the chat box.
During the code, why label was used during the training? Okay, so during the training of the discriminator model, you have to supply the code in order to calculate the loss. If in the supervised training, we have to supply the labeled model as well during the training, because it is going to generate some output, and unless and until you will not give the actual output, then you will not be able to calculate the loss. So in the supervised learning, we train the model so that by providing the label, so that it can calculate the loss after calculating it. Just a second. Simple augmentation versus GAN versus diffusion. Which model which prefer to generate? Achha, okay. So basically, if you want data augmentation, then no doubt simple GANs and diffusion models are better choice as compared to the simple augmentation. Why it is so? Because if you are performing simple augmentation, then in that case the features of the data are not going to change. For example, there is a diseased, there is a malignant or cancerous image. If you are just rotating it, then that cancer spot is not going to be changed, or malignancy is not going to be changed. So for example, if you are training your model for the crop leaf disease detection, and you are just rotating and flipping that diseased part, so in that case the features are not going to be changed. So your model is not going to get the diverse features. Now if I talk about the GAN versus diffusion models, so actually it depends upon the applications. Diffusion models are no doubt computationally complex one. So for the if you want some better resolution kind of images, then in that case you may use diffusion models, but they are a little bit costly because in the upcoming session, if you will go in details of the diffusion models, they are very computationally complex as compared to GAN, because in each epoch they have to calculate loss again and again. uh, you can so they are kind of 50 times computationally complex generally as compared to the generative adversarial networks. Yeah, any other one? Any other question from your side?
Hello. Yes, Krishna Chauhan. Actually, Dr. Ashish Tripathi just now disconnected just because of the network issue. He called me just now. So please, I request you, please, you ask your doubt, okay, in next session, okay, maybe in another day. Yeah, I will share. I will share this notebook and the PPT also. I will share everything related to this session. Okay, then I will share on the Canva, not an issue. Recording also, you will get the recorded videos. Yes, thank you. So because sir is disconnected, okay. So let's wind up the session here. And tomorrow that again the session that will start from 10 o'clock. Okay, fine. Thank you.